Now let us consider again the preparation of alcoholic AOH and the reactions of various species present in alcoholic AOH. Now alcoholic AOH is prepared by dissolving potassium hydroxide pellets in minimum amount of water and then adding rectified spirits to get a clear solution, then add anhydrous magnesium sulfate. It will deposit as a solid down the container. Now keep it overnight for one night, then the next day you decant it. Then what happens is that ethanol present in rectified spirit undergoes ionization to give C2H5O negative, that is ethoxide ion, and H positive. Now potassium hydroxide supplies OH negative, which will combine with the H positive to produce water. So H positive is removed from this equilibrium so that the forward reaction happens. Now the water formed will be absorbed by anhydrous magnesium sulfate to form MgSO4 7H2O, that is crystalline magnesium sulfate, and so the overall reaction of alcohol giving ethoxide is favored. So the medium will contain a larger amount of ethoxide, no hydroxide, because it is converted to water and that is absorbed by magnesium sulfate, and that will crystallize on the next day, so that we get a residue which is mainly magnesium sulfate 7H2O, so that the solution, the filtrate, will contain ethoxide ion along with the potassium ion and C2H5OH as the medium. So a solution of potassium ethoxide in ethanol, that is alcoholic AOH. Now consider an alkyl halide. Here a carbon chain connected to chlorine is shown. Now that carbon to which chlorine is connected is called alpha carbon. The next carbon is called beta carbon. Now due to the minus effect of chlorine, the electron pair along the sigma bonds move towards the alpha carbon. The impact of minus effect can be felt by the CH bonds, that is the CH bond where H is connected to the alpha carbon, and then the impact may be felt over the hydrogen connected to beta carbon. The bonding pair may be shifted towards beta carbon, and here also the bonding pair may be shifted towards alpha carbon, and this hydrogen gets a delta positive charge, and this beta hydrogen, we call it beta hydrogen because it is connected to beta carbon, so we can call it this hydrogen as alpha hydrogen. Now the delta positive charge over alpha hydrogen is greater than the delta positive charge over beta hydrogen, so naturally an ethoxide can attack the alpha hydrogen, and here the negative charge is shifted towards the H, means the lone pair of electron over oxygen atom, one lone pair will be shifted towards hydrogen. So establishment of weak bond between this hydrogen and oxygen, and then simultaneous shift of this pair of electron over the carbon, means the carbon atom alpha carbon takes up the bonding pair of electron in its orbital, and then simultaneous removal of chlorine as Cl negative. So chlorine is removed as Cl negative. Then we get a vacant orbital over carbon, and the species formed will be alpha carbon with a filled orbital and a vacant orbital. Now these two are hybrid orbitals, and they have the same energy, so one electron will be transferred to this orbital and we get what is called a diradical. Now the diradical will possess a very high potential energy, free energy. Due to the breakage of bonds here, the energy given to breakage of bonds is acquired by the radical and it is highly unstable, so there is no chance for formation of this diradical, which is unstable. Now another chance is the attack over beta hydrogen. Now before that, we compare the sizes of hydroxide and ethoxide. Now hydroxide is OH negative and ethoxide is O negative connected to C2H5. Now here instead of H we have C2H5 group, which is very high in size, higher in size than a hydrogen, so it can be considered as a bulky nucleophile or bulky base. So it cannot go near the alpha carbon to execute an SN reaction. So when this ethoxide group approaches this alpha carbon for a nucleophilic substitution, it will be repelled by a methyl group, so that ethoxide will not favor nucleophilic substitution. Now the only remaining chance is to attack the beta hydrogen. So this is alpha carbon, this is beta carbon. Hydrogen connected to beta carbon is called beta hydrogen. As usual, one of the lone pairs over oxygen atom will be donated to hydrogen, and that can be shown by starting the arrow over the negative charge and ending in between O and H. Now simultaneously the CH bond will be shifting in this direction, means the electron density will be gradually moving in this direction, and simultaneously the CCl bond will be shifting towards chlorine. We are able to get a transition state where there is partial bond between O and H, and this bond is partially broken, so broken bond, and here a partial bond is formed from this electron density, so a partial bond. Now this bond is stretched, so a dotted line. After the formation of this transition state, there is complete transfer of delta negative charge for the formation of OH bond. There is complete transfer of this partial bond in between alpha carbon and beta carbon, and we get the product as CH3CH2OH plus C double bond C, that alkene and a chloride ion. Now there is a rule called Saytzeff's rule, and during beta elimination we are actually eliminating a molecule of H and Cl from the structure. So it is removal of hydrogen and removal of chlorine. Dehydrohalogenation process it is called. So it is called a dehydrohalogenation because hydrogen and chlorine are removed and a pi bond is formed between the alpha and beta carbons. Now Saytzeff rule states that in dehydrohalogenation, the major product is that alkene which has the greater number of alkyl groups bonded to the unsaturated carbon. So when greater number of alkyl groups are bonded to the unsaturated carbon, there is a greater chance for stabilization by hyperconjugation. So let us see one example here. Now this is 1, 2, 3 and 4. So it is 2-bromobutane. So the starting compound is 2-bromobutane. Now here the functional group is bromine. It is connected to carbon 2 and that is called alpha carbon. Now the carbons adjacent to the alpha carbon are called beta carbon. Now here we have one beta carbon, here another beta carbon, and that is not denoted as beta dash because here it is a CH2 group and here it is a CH3 group. So these CH bonds are shown to indicate the eliminations occurring here. Now when beta dash H is removed, this bond will be shifting in this direction and the base here is ethoxide, so ethoxide OC2H5 minus will attack this hydrogen to form a bond. This bond will be shifting in this direction and Vr negative will be shifting in this direction. So double bond will be formed between alpha and beta dash positions. So we get CH3, CH3, CH, double bond CH, CH3, CH3, CH, double bond CH, CH3. Now you count the number of hydrogen atoms on the carbon connected to the unsaturated carbon. This methyl contains 3 hydrogen atoms. Similarly, this methyl contains 3 hydrogen atoms. So these 6 hydrogen atoms can give 6 hyperconjugation canonical structures, and greater the number of hyperconjugation canonical structures, higher is the stability. Now by a second route, the beta hydrogen may be removed. See, this bond will be migrating in this direction. Again, bromine will be removed and OC2H5 will be attacking the beta hydrogen to establish a bond. This bond will be shifting in this direction. Bromine will be replaced. It will be removed as Br negative. So we get a bond between alpha and beta position. So the product will be CH3, CH2, CH double bond CH2. Now here the unsaturated carbon is connected to a CH2 group and there only 2 hyperconjugation canonical structures are possible. So this is less stable and formed to an extent of 20%, whereas this one is formed to an extent of 80%. Now the corresponding parent compound may be considered as ethylene CH2 double bond CH2. Now this compound is formed from this parent by replacing one hydrogen by a methyl group and replacing another hydrogen by a replacing group. So we have 2 alkyl groups substituting the ethylene structure, whereas this structure is formed from ethylene by substituting only one hydrogen. So any one of these hydrogens may be substituted by a CH3 CH2 group and we get the product. So we can say this is a highly substituted alkene and this is less highly substituted alkene. There 2 alkyl substituents are here, whereas here only one alkyl substituent, that is ethyl group. So this is formed to a higher extent. This is the major product, a highly substituted alkene, and the reason behind the formation of this highly substituted alkene is the stabilization by hyperconjugation of the resulting alkene. Now the ratio between substitution and elimination, or elimination versus substitution. Now whether a substrate can undergo elimination or substitution depends on a large number of factors: the nature of the substrate, the nature of the solvent, the nature of the leaving group, the nature of the attacking nucleophile or base, and even temperature can affect the course of the reaction. Now a given molecule, given alkyl halide molecule can undergo substitution or elimination depending mainly upon the reagent used. If you are using alcoholic KOH, it is mainly ethoxide in ethanol medium, then we are getting the elimination product predominantly. But when we are using aqueous KOH, we are getting the substitution product where Cl is replaced by OH, so that the medium can affect the course of the reaction, the nature of the reaction. Ethanol is a less polar medium, and so in ethanol the reaction is one of elimination, that is beta elimination, whereas when we use aqueous KOH or NaOH, then chlorine is replaced by OH and the reaction is substitution, and there again substitution can occur by SN1 or SN2 mechanism, and this is decided mainly by the nature of the substrate. Usually primary alkyl halides, which cannot give a stable carbocation, react by SN1 mechanism, and it is said that a secondary carbocation is comparatively less stable, so that it is forced to undergo SN2 reaction than SN1 reaction, even though the SN2 transition state is a slightly crowded one. Now, tertiary alkyl halides react by SN1 mechanism. Now, if the attacking nucleophile, which can also act as a base, is bulky in character, is very large in size, then elimination is preferred over substitution, because a bulky nucleophile cannot enter into the region of the alpha carbon because it is surrounded by other groups. Apart from the leaving group, we have three groups around the alpha carbon, and when the nucleophile or base enters into the region, the three groups apart from the leaving group will repel this entering base or nucleophile. Then the entering base, if it is bulky, will suffer more steric repulsion, and then it will prefer a beta hydrogen rather than the alpha carbon connected to the leaving group. Now, such a reaction is shown by a bulky nucleophile, which is again a base, that is tertiary butoxide, and the structure is this one. It's a very bulky nucleophile. It cannot go near this carbon because of the steric repulsion between these methyl groups, and so it prefers the beta hydrogen. This is alpha and this is beta. So hydrogen connected to beta carbon is preferred by the bulky tertiary butoxide base. Here we call it a base. It is also a nucleophile, and here we call it a base because it is taking up a proton from beta carbon, a hydrogen as H positive from beta carbon. Now the negative charge, starting the arrow from the negative charge and ends in between oxygen and hydrogen. Then CH bond will be shifting towards this position between beta and alpha carbons, and simultaneous removal of Br as Br negative. We get CS2 double bond CH, CS3 plus tertiary butanol and Br negative. Now here elimination is favored because we are taking a bulky base or a nucleophile. And again, if a more substituted alkene is the product, then also elimination is favored. So a more substituted alkene, if it is the product, then elimination is favored over substitution. Now consider such a substrate where carbon atom is connected to two methyl groups, and then the alpha carbon is connected to two methyl groups, and then an isopropyl group. So all these groups are bulky, and so a nucleophile cannot enter into the region of the surrounding bulky alkyl groups towards the alpha carbon. So the nucleophile or base prefers the beta proton, and here this is the beta carbon, and hydrogen connected to beta carbon is called beta proton, and this beta hydrogen is being attacked by the ethoxide base, so there is simultaneous shift of this bonds, and we finally get this structure. We can call it 1, 2, 3, 4. So 2,3 dimethyl butane. It is in fact a most highly substituted alkene where all the 4 hydrogen atoms of ethylene are replaced by methyl groups, and you count the number of carbon atoms, to count the number of hydrogen atoms connected to the unsaturated carbon. So you count the number of hydrogen atoms on the carbon directly bonded to the unsaturated carbon. Here 3, 3, 3 and 3. So altogether 12 hyperconjugation or canonical structures are possible. 12 hyperconjugation canonical structures are possible, and one such form is shown here. So 12 such structures, and this is highly stabilized by hyperconjugation. So if a more substituted alkene is the product, then elimination is favored over substitution. Now nature of solvent can affect the course of the reaction, means the nature of the solvent can decide whether a reaction should happen by elimination mechanism or a substitution mechanism. A less polar solvent favors both SN2 and beta elimination that you have seen earlier. Why? Because a less polar solvent has a low dielectric constant, and dielectric constant is the capacity of the solvent medium to hold the ions separately, and if dielectric constant is low, polarity is low, we say, and the medium cannot hold the ions separately, so that the ions will attract and form the corresponding salt and will be precipitated. And the best example for such a reaction is the Finkelstein reaction between methyl chloride and sodium iodide, and there the medium is diacetone, which is less polar, whose dielectric constant is 20, so its polarity is low. For water, the dielectric constant is 80, it is very high in polarity. Now there the mechanism is SN2, and again in alcoholic AOH, alcohol, which is a less polar solvent, the dielectric constant is low, and so a less polar medium favor both SN2 and E2 beta elimination reaction. And there again, if the nucleophile is or base is very bulky in size, then the SN2 reaction is prevented, and if the substrate is also having bulky groups, then again SN2 reaction is not favored, and E2 reaction or beta elimination reaction is favored. So less polar medium favors both SN2 and E2, and as the polarity of the medium is increased, SN2 is favored over beta elimination. For example, alcoholic AOH favors elimination, whereas aqueous KOH favors substitution. So in alcoholic AOH, the main reaction is elimination, and alcohol is a less polar medium. And if we are adding water to the alcohol medium, or if we are taking aqueous NaOH or KOH, the main reaction is SN2 reaction or a given substrate which is primary in character. So that we can say SN reaction is favored when the polarity of the medium is increased. Now coming to another set of reactions of the alkyl halides. Now the first reaction is the reaction with magnesium metal in dry ether. Ether is diethyl ether, which is a solvent. So you treat alkyl halide with magnesium metal, and magnesium is a divalent metal. Magnesium has got two free valencies, we can say. Now Rx molecule dissociates such that there is a valency over R and there is a valency over X. Now magnesium with its two hands should be holding R and X. So we get RMgX, Rx plus Mg giving RMgX. Magnesium with its two valencies hold R and X. Example, CS3Br plus Mg giving CS3MgBr. It is called methyl magnesium bromide. Now here magnesium, the oxidation state is +2, so that the carbon of R group has an oxidation state of -1, and X also has an oxidation state of -1. And then RMgX can ionize as R negative and Mgx positive in aqueous medium, where RMgX reacts with water because R negative part can combine with the H positive part to produce hydrocarbon RH, and the Mg combining with the OH producing NgOHX. So for the reactions of Grignard reagent is a reagent from which we can prepare a large number of compounds. So for the reactions of Grignard reagents, anhydrous ether is necessary, because if it is containing traces of water, then the Grignard reagent will be reacting with water to produce alkane. So formation of Grignard reagent is one reaction of the alkyl halide with metal. Now another set of reactions called Wurtz reaction, that is reaction between alkyl halides and metallic sodium, again in dry ether medium. Now the reaction is Rx plus 2Na and XR. We write it as XR. To understand the reaction, you put X and 2Na in a box, then the 2NaX is removed and we get R valency connected to valency of R. RR is a hydrocarbon. Now if the same alkyl halides are used, you get only one hydrocarbon. If you are using say methyl chloride, 2 molecules of methyl chloride, and here written as ClCH3 plus 2Na giving 2NaCl, and CH3CH3, that is ethane. And if you are using two different alkyl halides, then we are able to get 3 different alkanes. For example, a mixture of methyl chloride and ethyl chloride reacting with sodium metal in dry ether medium. 2 molecules of methyl chloride can react with metallic sodium, giving CH3 bond CH3, that is ethane. Then 1 ethyl chloride reacting with another ethyl chloride with metallic sodium in dry ether medium, producing this ethyl group connected to this ethyl group, that is butane. Then a mixed reaction between ethyl chloride and methyl chloride, producing 1, 2, 3, that is a hydrocarbon containing 3 carbon atoms, that is propane. So much about the study of haloalkanes. Now we shall pass on to haloarenes.